Okay, I think it's 10 o'clock, so let's get going. Welcome everybody to the HAI Weekly Research Seminar. I'm Noah Goodman. I'm an associate professor of psychology and computer science at Stanford. I'm extremely thrilled to introduce my colleague, Toby Gerstenberg. Toby is an assistant professor of psychology here at Stanford, and he leads the Causality in Cognition lab, which studies the role of causality in people's understanding of the world and each other. In his talk today, Toby is going to argue that people's knowledge of the world is organized around causally structured mental models, and that much of human thought can be understood as cognitive operations over these models. This will allow him to highlight the pervasiveness of counterfactual thinking in human cognition. Before we begin the presentation today, just a couple of logistical details. You can use the QR code on the screen to ask questions through Slido, or you can click on the link that will be in the chat shortly to get to Slido. At the end of Toby's talk, I'll be drawing questions from Slido and offering them for his comments. Toby, thank you so much for joining us, and go ahead and take over.
Cool. Well, thank you so much for the kind introduction, Noah, and also thanks to HAI for inviting me to present, and to all of you for joining me today. I'll put myself in a little corner here. Yeah, so the title of my talk is Going Beyond the Here and Now, Counterfactual Simulation in Human Cognition. And as Noah already said, I'm in the Causality and Cognition lab here at Stanford University, and our lab studies the role of causality in people's understanding of the world and of each other. So we're interested in how people learn about the causal structure of the world, how once they have it, how they can reason about the world, so make predictions about the future or inferences about the past, and also how these capacities ground out in the kind of judgments that we make in our everyday life, such as assigning responsibility to others. When I make a Wordle of some of the paper titles that I've written, this is sort of what comes out. And as you can see, causality, responsibility, and counterfactual are sort of big themes in my research. Responsibility is interesting and important, I think, because many of the problems that we face as society today are arguably problems of responsibility, so including problems of collective responsibility, like the problem of global warming, political participation, polarization, and also basically the development and employment of ethical AI systems, things that HAI, of course, cares a lot about. Studying responsibility is also interesting just from a scientific perspective, because there are a lot of challenges that arise when trying to understand basically how people assign responsibility. So one of the goals that my lab is working toward is building a computational framework for understanding responsibility. And to do so, I think we need to be able to answer at least two questions, one of which being what causal role somebody's action played in bringing about the outcome, and the other one being what the action reveals about the kind of person that the person is. For this first question, we need some intuitive theory of how the world works so we can relate actions to outcomes. And for the second question, we need an intuitive theory of how people work so we can go backwards from the actions we observe them taking to the underlying mental thoughts that gave rise to those actions, such as beliefs and desires and intentions. I've worked quite a bit on the sort of intuitive theory of people part, but in this talk today, I'm going to be focusing on causality. And the work of Judea Pearl has been a key inspiration for me on that front. And he has argued that understanding causality is really key for building truly intelligent machines. So his prescription for progress in artificial intelligence is teach machines to understand the question why. And I also want to put in a quick plug here for a wonderful book that just came out last week by my PhD advisor, David Lanyado, explaining the evidence, how the mind investigates the world. And a lot of the themes that I'm exploring in this talk are also explored in depth, basically, in this book. One of the key themes that's going through all of my research is basically the idea that people build mental models of the world. And that idea has been around for a long time, but sort of more recently it's been fleshed out and made a little bit more concrete, particularly when applied to the idea of how people build mental models of the physical world. And one idea here is that people's mental model of the physical world might in important respects be similar to the kind of game engines or physics engines that we have in modern computer games, basically. So the idea is that we take in the world through our perceptual senses, and that we build an internal representation of the world, where we then have, for example, representations of objects and agents in that world, and where those objects have attributes such as positions, velocities, and materials. And then we can use that internal model of the world to simulate, to run, for example, predictions about what's going to happen if I toss this ball like against the tower and whether or not that eagle is going to fall. And if I have such an internal representation of the world, I can use it for different purposes. I can, for example, decide whether this tower of blocks here is going to fall or not, so make a prediction about the future. Or I can make an inference about an unobserved state of the world, such as, for example, here figuring out how heavy this green block must be, knowing that the tower is stable at this point. I can also use it to make judgments about causality. I could, for example, decide to what extent this green block there at the bottom is responsible for the tower stability by simulating what would happen if that tower were removed. And it can serve as a guide for actions, for planning. So where would I need to place a block, for example, in that scene in order to stabilize the tower? Judea Pearl in his work has basically proposed a causal hierarchy, or sometimes he calls it the ladder of causation, where these different capacities are on different levels in terms of basically how much causality is involved to be answering questions on that level. So on the first rung of that ladder, it's the ladder of association, basically just figuring correlations between things. So here we could answer questions such as what a symptom tells us about a disease. On the second level is the level of intervention, where we think about basically the consequences of actions, hypothetical actions that we could take. So what if I take aspirin, will my headache be cured? And then on the highest rung, on the third ladder, or the third rung of the ladder of causation, there's the level of the counterfactuals. So those might be questions about whether it was the aspirin that actually stopped my headache, or whether my headache stopped because of some other event that happened. And it's this level of causation that I'm interested in. And that's the level at which Pearl also argues where we understand and answer why questions. So in my talk, I'm going to be focusing on two sort of larger projects that my lab's been working on. The first one is about causal judgments. And the second one is about multimodal inference, so how people draw inferences about the past from combining visual and auditory evidence. But let's start with the causal judgment part. So in this part, I'm interested in exploring how people make causal judgments about physical events. And now imagine that you're a participant participating in this experiment, and I'm going to ask you whether you think that ball A caused ball B to go through the gate. So these balls are going to be entering into the scene, and there's the gate here on the left-hand side. So I can't do a live poll here because I can't see you, but if I were to ask you, I'm pretty sure that most of you would say that yes, ball A caused ball B to go through the gate. And here's what we think is going on in people's minds when they decide to give that judgment. So we've been developing for a while now the counterfactual simulation model, and it was published earlier this year in Psychological Review. And according to that model, what people are doing is they're first taking into account what actually happened. So that's the sort of non-controversial part. So people see that A and B collided and that B ended up going through the gate. But in addition to that, people also simulate what would have happened in the relevant counterfactual situation. So you're basically imagining what would have happened if ball A had been removed from the scene, and then trying to extrapolate where ball B would have ended up in this counterfactual situation. And the idea is then, the more certain you are that the outcome in the counterfactual situation would have been different from the outcome that actually happened, the more you're going to say that, yes, A caused B to go through the gate in this case. So this idea of basically thinking about causal judgments as counterfactual contrasts over generative models of the world is very much inspired again by the work of Judea Pearl, where in his work, the knowledge that people have of the world is basically represented in terms of, for example, causal base nets or structural equations. And the counterfactual operation that I then put on top of that model is the do operator. So what we do instead now in this case of thinking about people's causal judgments about the physical domain is we assume that the generative model is now like a physics engine, in this case, like a probabilistic program. I'll go into the probabilistic part in a moment. And the counterfactual operation that we define over this representation is something like then a remove object operator. So basically rerunning the world and imagining what would have happened if that object had been taken away. Now, this might seem fairly intuitive to you, and you might ask even like, oh, what else could you possibly be doing instead of doing that? So there's a whole class of theories in the philosophy of causation and also in psychology that are called actualist theories of causation. And what those theories postulate is basically that you can do away with that part, with the counterfactual part, that in order to understand causal judgments, you only need to focus on what actually happened, no need for counterfactuals. The best worked out account of this idea in psychology is by Philip Wolff, and it's called the force dynamics model of causation. And according to that model, what people do is they represent the forces that are at play at the time of a causal interaction. And the configuration of these forces basically determines whether there was causation or not. So let's apply this to our case here. So there's a force associated with the patient, like ball B in this case. And then there's a force that the agent impacts on the patient. So that's the agent force here, force A. As a result of these two forces, I have a resulting force R. And then there's an outcome state here, an end state, and whether or not B reached the gate. And so this configuration of forces and B reaching the end state maps onto cause in this force dynamics model. So the force dynamics model in this case would also here say, yes, A caused B to go through the gate. And just to make clear what the distinctions between these two accounts are, according to the force dynamics model, the intuitive theory that people have is represented in terms of force vectors. And then there's a direct link basically from this intuitive theory to causal judgments. I only need to look at the forces that are there at the time of causal interaction, and that's all I need to make a causal judgment. I could also make counterfactual simulations by, for example, imagining what would happen if one of the forces wasn't present, but that's not critical for basically making causal judgments. According to the counterfactual simulation model, we think that people's intuitive theory is probably better captured by something like a physics engine, like in the head. But maybe the more important difference is that we think that in order to go to causal judgments about particular events, whether one thing caused something else to happen, you have to go through this process of counterfactual simulation. And in the following, I'm going to try and motivate this account. So the first argument is just like an argument of generalization. So imagine that I was saying at the beginning that one thing that my lab works toward is developing a computational theory of responsibility. So to do so, I need some model of causation that doesn't just work in physics, but can also generalize to other domains. So here's just an example for the kinds of causal judgments that we might reach in our everyday lives. So we could say that the fall of Lehman Brothers caused the financial crisis, that my housemate's failure to water my plants caused him to die, or that realizing that he forgot his wallet at home caused him to go back. So you probably wouldn't use the cause construction, but nevertheless, those are all perfectly plausible and sensible things to say. But it's unclear how, when we represent these kinds of causal relationships in terms of forces. And maybe a counterfactual theory defined over a generative model of the world can more flexibly apply to these kinds of cases as well. Another big plus of the theory that we've been developing is that it allows quite naturally to generate quantitative predictions. And here the idea is that, as you were saying, people's causal judgments is a function of basically how sure they are that the outcome in the relevant counterfactual situation would have been different from what actually happened. So now people don't have ground truth access, right, to what the counterfactual would have looked like. But they have to use their intuitive domain knowledge, in this case, to simulate what the relevant counterfactual outcome would have been. But we assume that people cannot do that perfectly, right? And one way to capture that is by assuming that people draw samples, basically, in their mental model of this world, and that now the samples that they draw are somewhat noisy. So one way to make this concrete is to say, imagine that when simulating where ball B would have gone, we introduce a little bit of noise into ball B's motions at each point in time. And now this would be one sample that we draw, one simulated sample. And in this case, yeah, ball B would have missed. So we would say, yeah, A caused ball B to go through the gate. And now we can draw a few more of these samples. And here the idea is that we should be fairly certain that A caused B to go through the gate, because in all the counterfactual simulations that we draw in our mind, ball B would have missed. But now if you look at a slightly different case, where again, what actually happens is A and B collide and B ends up going through the gate. But this time the counterfactual is less clear because the ball is headed right to the goalpost here. And now when I draw these noisy simulations, right, in some cases, maybe ball B would have missed, but in some cases, it's also possible that ball B would have gone through the gate. And so in this case, because there's a chance that ball B would have gone through, even if ball A hadn't been there, I should be less inclined to say that, yes, A caused B to go through the gate. So that's the basic idea. So we tested this experimentally, and here I'm just showing you 3 examples of clips that we've used. So this is an example here where it was pretty clear that ball B would have missed if ball A hadn't been there. This is a situation where it was unclear. And this is a situation here where ball B would have gone in even if ball A hadn't been present in the scene. And then in one experiment, we just asked a group of participants to answer a counterfactual question. So we just asked them, would B have missed the gate if ball A hadn't been there? And here participants are fairly sure that it would have missed. Here they're kind of very uncertain. And here they're pretty sure that ball B would have gone in even if ball A hadn't been present in the scene. And then we asked a separate group of participants who we didn't tell anything about counterfactuals, a question about causation instead. So whether A caused ball B to go through the gate. And we found that those answers very closely align with the counterfactual judgments of this other group of participants. And we can also use the counterfactual simulation model, which again draws sort of noisy samples about what would happen if ball A wasn't present in the scene. And that also yields a very similar pattern of results. So these were just 3 of the clips that we showed to participants. In total, we showed participants 18 different video clips here. And what the scatter plot is showing, it's basically on the x-axis here, the average counterfactual judgments from one group of participants, and on the y-axis, the average causal judgments from another group of participants. And you can see that these align very closely with one another. However, when we published this work, there was some pushback from a reviewer who said, well, all the clips that you used in this experiment, actually something different happened in each of those clips. So it's possible in principle that you could come up with an account that is still trying to explain the variation in people's judgments just in terms of what actually happened. We tried to develop such an account and sort of failed, but we thought the stronger test for the necessity of counterfactuals that we could come up with was basically an experimental test. So here's what we did. Again, imagine participating in this experiment. This time I'm going to ask you whether you think that ball A prevented ball B from going through the gate. So here's what's happening. I'll play the clip once more. So again, when I normally ask participants here in this, or not participants, but audience members, like they tend to say in this case that no, A didn't prevent B from going through the gate. Because they think, well, B would have ended up somewhere up here in the corner if ball A hadn't been there. So here's a different clip now from the same world. And this wasn't a glitch. I didn't tell you anything about these 2 different objects, but in fact, it's actually like a teleport, and that only works for ball B. So if ball B enters into this teleport entry here, it exits out of this exit in the same way in which it entered. So you might have like a one-shot learning in this case, like an aha moment very quickly. So now that you know this about the world, I can show you the exact same clip that I've shown you earlier. But now you're going to say that, yes, in fact, A did prevent ball B from going through the gate. Because now your counterfactual has changed. Whereas previously you thought the ball would end up here. Now you're basically realizing, oh no, it would have gone through this entry here and come out of the exit and would have gone through the goal. So the fact that I can show you exactly the same video twice and your causal judgment shifts dramatically between the 2 instances demonstrates, I think, very clearly that it's not going to be possible to reduce causal judgments to basically just what actually happened. It's the counterfactual that matters, namely your belief about what would have happened in the relevant counterfactual situation. But here, the relevant one might be one where basically we're simulating what would have happened if ball A hadn't been present in the scene. So we don't need a fancy teleport to do that. We can also move a brick around, like in here. So basically, in this clip up here, people don't say that A prevented ball B from going through the gate because the brick would have blocked it. Whereas here, people say that, yes, A did prevent B from going through because the brick was moved out of the way here. And in a similar way, we can do that for causation as well. So in this case here, people say that, yes, A caused B to go through the gate because B would have been blocked. And here they don't really say that A caused B to go through the gate because the brick would not have blocked ball B. And again, in each of those pairs, the actual interactions between the balls are identical. Okay, so hopefully this was somewhat convincing. But we can find even stronger evidence basically with this account, because the account makes some predictions about basically what people are doing when they're making causal judgments, namely that they're engaging in this process of counterfactual simulation. And one way to test that is by doing eye tracking, by seeing what is it that people are looking at when we ask them to make causal judgments. So that's what we did. We went back to these like very simple cases where we just have like ball A and ball B, no teleports involved. And we ran this experiment in different conditions. The conditions just differed in terms of what questions people were asked to make about the video clips. So in this, what we call the outcome condition, we asked participants to make a judgment about the outcome at the end of the clip. So in this case, whether they think that ball B completely missed the gate. And I'm going to be playing this clip at half speed and sort of live narrate a little bit where the participant is looking at, which is indicated by the blue dot. So here, the participant is going back with their eye movements between ball A and ball B. So they're kind of focusing on ball B right now, trying to anticipate where ball B is going to end up hitting the wall. Still looking at ball B. And that's basically it. So mostly looking at ball B because that's all they need to know in order to be answering this question here. So now if we take another participant who watched exactly the same video clips, but this time was asked a causal question. So in this clip here, whether ball A prevented ball B from going through the gate, you'll see that the eye movements look very different, like in this case. So as you can see, this participant doesn't just look at ball B, but they try to simulate basically where ball B would have ended up if ball A hadn't been present in the scene. I'll just show that once more. And also consistent with the idea that people are drawing sort of several noisy samples or simulations that try to anticipate, again, where ball B would have ended up if ball A hadn't been present in the scene. And what's very nice about the setting, I find, is that so the idea that counterfactuals and causality are closely linked to one another has been around, of course, for a very long time. But very often how it was explored in psychology is by basically giving people vignettes, so written descriptions of certain scenarios, and then asking them to make causal judgments. But in those scenarios, you often have to explicitly stipulate, basically write down what the relevant counterfactuals would have been. Whereas here in this setting, we don't need to do that. In the experiment where we ask people to make causal judgments, we don't tell them anything about counterfactuals. We don't tell them like, oh, when you're thinking about whether ball A caused ball B, maybe you want to think about what would have happened if ball A hadn't been there. We don't do that. We just ask them, give us a causal judgment. And the fact that people are spontaneously engaging in these kind of counterfactual simulations is then even stronger evidence, basically, for the link between counterfactuals and causality, we think. So these were just two videos that I showed. One way of quantifying a little bit more to what extent people are engaging in these kinds of looks is by looking at the endpoints of people's saccades. So saccades are these fast eye movements from one point to another. And then basically looking at where those land. So what we did is we took the time between when the balls entered the scene and collided with one another and looked at all the saccades that people produced and looked whether the endpoints of these saccades ended up basically close to the path that ball B would have taken if ball A hadn't been present in the scene. And what we see is that in the causal condition, there's a lot of these counterfactual saccades are being produced. Again, here just for one clip, but it holds across all the clips in the experiment. And many more than, for example, in this outcome condition here. Okay, so this was even more evidence that people, well, in some sense, the most direct evidence, I guess we could find that people engage spontaneously in this counterfactual simulation when making causal judgments. So what about more complex situations, you may ask? So far, we've been dealing with fairly simple ones with 2 billiard balls. So now we're going to be looking at 3 billiard balls. That's as complex as it's going to be getting in this talk here. But let's take a look at that. So here's a simple causal chain situation where A bounces into B and then bounces into E. And when we asked participants to give us judgments in this case, in one of the experiments, we asked them to what extent ball A was responsible for E going through the gate and to what extent ball B was responsible for E going through the gate. We've also done this asking about, to what extent did it cause it? It doesn't really make a difference how you ask the question here. These are the judgments that people give us. So they give a pretty high judgment for ball A in this case, but still like a pretty high judgment for ball B as well. And from all I've been telling you up until now, this is sort of a little bit surprising because if what people are doing is just basically imagining what would have happened if the ball hadn't been present in the scene, and then seeing like basically given a causal rating to the extent that the presence of the ball made a difference to whether or not the outcome happened, ball B should get a very low rating in this case here, because even if ball B hadn't been there, E would have still gone through the gate, A would have still knocked it through. So it's a problem for the account that I've been telling you up until so far, that the rating for ball B is so high here. Here's another clip that we used in that experiment, the one that philosophers love. It's called double prevention. And And you can probably see why it's called double prevention, because here ball B prevents ball A from preventing ball E from going through the gate. Again, very tricky to kind of show with text, but pretty easy to show basically in this kind of visual representation here. In the video. And what we found in this experiment is that the causal judgment that participants gave to ball B was fairly low in this case. Right? And here the question is, why so low? Because if we ask another group of participants to say, would E have gone through the gate if ball B hadn't been present? They say, no, it wouldn't have gone through. And accordingly to this simple idea, B should get a high causal rating. So this is sort of what I looked like for a few months. I was at MIT at the time, and then actually came to visit Noah at Stanford to try and figure this out. And we kind of did, I think, at least to the extent that I'm going to be telling you now, and you can make a judgment whether you think we did or not. And one of the things that I did do in that time was just reread like a bunch of philosophy that I had already read, but then sort of, reread because I was trying to figure out basically how to make sense of this. And there was a passage here in Jim Woodward that I came across again, where he basically says that some of these intuitions behind the geometrical mechanical approach, so that's this more force idea of causation, can be captured by thinking in terms of spatiotemporally organized difference-making information. So the idea of thinking about basically counterfactual dependence at a finer level of granularity. And this idea in similar ways had also been endorsed by David Lewis and Chris Hitchcock. So how can you make this concrete? So what I've been telling you up until now, I'm now going to call the idea of weather causation. So the idea there is to say, to ask the question whether the outcome would have been qualitatively different if ball B in this case, it's the one that I'm asking about, had been removed. So the relevant counterfactual operation is removing a ball and then simulating whether ball E would or would not have gone through the gate, like in this case. And now introduce a different notion of causation, or different aspect of causation that we call Hull causation. And here the idea is that what you're doing is you're still running a counterfactual simulation, but now a slightly different one. So you're imagining a small perturbation, like to the object of interest, in this case, changing ball B somewhat, and then simulating whether the outcome would have been different from what actually happened. And where now the outcome is more finely construed, such as E going through the gate at this point in time with that velocity, and so on. So if you allow us to make this move, then we can kind of make sense of people's judgments in these cases, and actually like a number of other cases that I'm going to show you in a moment. So why do participants give such a high rating to ball B here? Well, because ball A here, because it was both a weather and a Hull cause of the outcome. If A hadn't been there, E wouldn't have gone through the gate. But also if I changed A little bit, E would have gone through the gate differently from how it actually did. For ball B, it wasn't the weather cause. If it hadn't been there, E would have still gone through. But if I perturbed B a little bit, E would have gone through the gate differently from how it actually did. And because it's only a Hull cause and not both a Hull and a weather cause, people might give it a lower judgment of causal responsibility here. And then for the case of double prevention, ball A here is neither a Hull nor a weather cause, whereas ball B is a weather cause. If it hadn't been there, A would have knocked E out of the way and E wouldn't have gone through. But even if I apply a small perturbation to ball B, E is still going to go through the gate exactly in the same way that it did. So B was not a Hull cause of E's going through. And if people care about both of these aspects of causation, we can understand why their causal judgment is lower in this case here. So that's the basic idea. In the experiment, we had a whole bunch of different cases, like 32 different cases. And we find that this counterfactual simulation model that is equipped with multiple aspects of causation accounts well for people's judgments. And one important idea that I should highlight here is that whereas previous work, mostly in philosophy, has argued for these sort of fundamentally different notions of causation, that there's a dependence notion, like a counterfactual account of causation, and then there are the production notions of causation. So causation is about the physical transfer of force, for example. What we do in this work is we try to unify these different frameworks. So instead of thinking about multiple fundamentally different concepts of causation, we just argue that there are different aspects of causation, but that each of those aspects of causation can be understood as a counterfactual operation, basically on the generative model of the world. And here it's the physics model, that's the generative model. And the different kinds of counterfactual operations are, for example, removing a ball or slightly perturbing a ball, and then seeing what the consequences of that counterfactual operation would have been. And you can read much more about it if you like in our psychological review paper. So to briefly recap this sort of first part of the talk. So I've introduced the counterfactual simulation model of causal judgment, where we have shown that causal judgments are well explained by the observer's beliefs about whether the candidate cause made a difference to the outcome. that counterfactual contrasts are necessary for explaining people's causal judgments, either via the teleport or moving the brick out of the way. We showed this. That people spontaneously engage in counterfactual simulation when making causal judgments. We've shown that via the eye tracking evidence. And that people consider several aspects of causation when making causal judgments. And that these different aspects are really brought out when looking at these more complex cases. Just want to show a few areas in which we've taken this work like afterwards. We've also basically used our counterfactual simulation model to try to explain the mapping between different causal expressions and the events that happen in the world. So what people think, for example, when somebody said that something caused something to happen or enabled it to happen or affected it to happen, basically providing a semantics of these different terms in terms of the different aspects of causation that our model postulates. And then also assuming that people are pragmatically choosing expressions that are most informative, basically, about the events that happen in the world. We've also applied the model to thinking about causation by omission. So when something happened because something else didn't happen, again, something that's natural to model within this idea of counterfactual simulation. And also exploited basically related concepts, like we've seen these brick towers already at the beginning. So if you think of physical support as essentially meaning preventing from falling, right, then it becomes a causal notion. And you can ask whether people's judgments about how responsible this black brick here is for the red bricks laying on the table, whether you can basically understand this in a similar way by people imagining what would happen if that block wasn't present and then simulating the outcomes of this hypothetical intervention. And we've also used these ideas to explore people's moral judgments in these simple kind of vignettes here that are inspired by these Hyder and Simmel moving shapes, and where we ask people how bad it was what one particular agent did in a scene, and finding then both that it matters basically the extent to which they infer that the agent exerted effort in bringing about the outcome, which is indicative of their desire to cause this bad outcome, and also again the causal role that they played, whether or not the outcome would have happened irrespective of what they did. Okay, so this was the first part here on causal judgments, and now I'm going to be talking about multimodal inference. So the question of how people figure out what happened in the past by trying to combine both evidence from vision and sound. And so while I was a postdoc at MIT, for a long time I had this item on my to-do list that basically just said causality and sound. And it's not a very actionable item on the to-do list, but I was basically kind of just intrigued and puzzled by this everyday observation that there's so much that we learn about the world basically just by hearing and the inferences that we can draw from that. And so one kind of puzzling example of that maybe you didn't know about is you actually have the capacity to hear temperature. So you're going to demonstrate that with you. So I'm going to be playing you two different sounds, and I'm going to ask you which one of the sounds was cold water being poured into a glass. So one is cold water, the other one is hot water. Which one is which? So this was one. This was the other. And again, if this was live, I've done this a few times now. It's astonishing how good people are, at this task. The first one was the cold water, and the second one was the hot water. And not only adults can do that, even young children can do that too. So starting at around age of 6 to 11, they reliably pick out the right sound, like in this false choice scenario here. More generally, right, there's a lot that we can infer from the world. Here we have Sherlock. From what we see and what we hear. So for example, just from visual evidence, you might have a pretty good idea what happened to this Coke can here. And maybe you can also tell what happened here, right? That there was a sausage here and that a dog must have picked it up because it left a paw imprint behind. So sometimes we only have visual evidence, and forensic scientists might only have visual evidence, but sometimes also we have both visual and auditory evidence. So here in the case of the assassination of JFK, right, some people heard and reported that one gunshot was fired, whereas other people reported to have heard multiple gunshots coming from different directions. And then, of course, that would suggest something different about what must have happened, like depending on which of these two scenarios you think was right. So I'm interested in that question of how people combine visual and auditory information to figure out what happened. And much of the prior work in this domain is sort of taking a statistical approach to this idea. And much of it has been sort of more in the perception part. So where the idea is that, yeah, you have evidence from multiple sense modalities, and maybe you're integrating them optimally by taking into account the uncertainty that is associated with each source of information. Basically doing something like an uncertainty-weighted averaging of the different pieces of information. So I'm more interested now in this kind of more reasoning-y part, where the idea is that these different senses give us some evidence about basically what happened in the world, and they communicate essentially through this internal representation like of the physical world in this case. So eventually that item got to actually sort of a more concrete idea about how I could be testing this idea of people drawing inferences from both visual and auditory evidence. And what I came up with is basically this Plinko box here. So I'll give you an example. So this is the box. The ball here can be thrown into one of these three holes at the top. There's going to be a little beep sound that plays when the ball is dropped. And then you'll hear the sounds as it collides with the obstacles and then lands in the sand. So I'll just show you a few examples here first. And we do that in our experiment as well. We show participants some videos so they get a sense for the physical parameters basically of the setting. Okay, so now you have a sense for how this box works. I could ask you again, for example, here now I put the ball at the top and I ask you where you think the ball will land. How we did that in our experiments is we had participants click 10 times. So they could also basically give us bimodal distributions, like if they wanted to, because maybe here it's unclear whether it's going to end up on the left or the right side of this triangle here. We then take all of those responses and can turn them basically into a density that gives us a summary of participants' predictions, like in this clip. And here's also the ground truth. So the ball would have actually ended up all the way over there. Here are some examples from individual participants. So this participant, I guess, clicked 5 times here and 5 times there. This participant clicked 10 times here, was very sure it's going to land exactly in the spot. But then we also sometimes get participants that actually indicate the uncertainty. Here's sort of like a bimodal with uncertainty, and here there's sort of a unimodal distribution with uncertainty. Again, we then take all of those and turn them into densities. And here on the left-hand side, you see now an example of these are now densities of participants' responses for the 3 possible locations in which the ball could be dropped. And now, when modeling that, I'll move to one particular example here. The idea is, again, how do we go from a model that is essentially deterministic, like the physics engine at the beginning is deterministic, to a representation that is probabilistic? And it's a similar idea, like with the billiard balls, that we essentially inject noise into the system. So assuming that there are some sources of uncertainty that the participants have, and that we can capture these sources of uncertainty by introducing noise, and then assuming that people draw several samples in that noisy representation, like of the physical scene, then yields basically a probability distribution over possible outcomes. So here we assume 2 different sources of noise. Participants might be uncertain about, how exactly the ball is being dropped. And that then allows us to get sort of like bimodal distributions here, because they might be unsure about whether it's going to go on the left side or the right side of this tip of the pentagon here. And then we also introduce collision noise. So the idea is when the ball collides with an obstacle, people might not be exactly sure how that collision is going to play out. So we allow for some noise basically in the magnitude of the ball's collision after whenever it collides, basically. So introducing 2 different sources of noise, and then sampling many times, basically then, in this case, yields a distribution from the model that's quite similar to the distribution that we get from people. To compare basically the model with people, I'll do a simple thing here. I'm just going to be looking at the means of the distributions that we get from the model for each hole. So these are the 3 different holes here. And compare that to the mean judgments from participants in this case. So again, for the 3 different holes, these would be the means of those distributions here. And then I'll put them on a scatter plot here where the width of the scene was 600 pixels. So that's what the model says. And here also on the 600 pixels, that's the mean judgment from people. And if we do that for all the different clips that we had in the experiment, we get a very close alignment between the simulation model and people's mean judgments in this case. If we just use the ground truth, like instead of this noisy simulation model, that doesn't account as well for participants' judgments, like in this case. And also if you were to use a simple heuristic, where we just assume that people think like, oh, the ball's just going to end up under the hole, basically, that again accounts for some of the variance because the ball tends to end up on the right-hand side if it's dropped in this hole here. But there's a lot of variance, of course, that's missing from the simple heuristic. So that was the forward model, the forward direction. And we can then go the other way around as well, right? So we can put the ball at the bottom and ask in which hole the ball was dropped. How we did that experimentally is we put text boxes over the 3 different holes and then just asked people to put in numbers that would add up to 100. So indicating their degree of belief that the ball was dropped into, one of the 3 different holes. So now how do we do inference in this task? Basically, in the same way that you always do inference, like in a Bayesian way. So you have the forward model, and then you try to invert that model. And in this case here, you're basically simulating, well, where would I expect the ball to end up if it was dropped in hole 1? And I get some distribution. Where would it end up if I dropped it in hole 2? And where would it have ended up if I had dropped it in hole 3? And then I'm comparing basically these distributions to what basically happened in the actual situation. So the idea is that we get like a likelihood function that essentially just takes into account the distance of each sample that I drew in the simulation, like to where the ball actually ended up. And so a good candidate hypothesis is one where basically all the samples that I drew end up pretty close to where the ball was in the actual situation. So if we then just assume a uniform prior over the 3 different holes at the beginning, we can get to the posterior, so people's belief in the ball being dropped into one of the 3 different holes. And here basically the bars show people's average posterior judgments or their beliefs that the ball was dropped into these different holes. And so they think it was most likely in this case that the ball was dropped in hole 3. And on top of that, here are the model predictions in these little circles, and the model captures people's judgments here. Again, we can then compare model predictions with people's judgments just by correlating basically the responses like to the different holes with one another. And the simulation model does a good job of capturing people's inferences here. And we didn't have to introduce any new parameters here because we just had fitted the noise parameters to people's predictions and then took that same model to model people's inferences. We can also directly just take people's predictions that we have from the forward direction and basically correlate those with participants' inferences, and it also works very well. We again also contrasted this with a simple heuristic that just assumes that people pick a hole that's closest to where the ball ended up being. And that simple matching model, again, captures some of the variance in participants' responses, but is not as good as the simulation model. So far we've only dealt basically with the visual dimension, and now we're going to add basically audition like into the mix. So the basic idea here was to cover the box up first and then drop the ball so participants would hear the sounds that the ball made when it was being dropped. And then we reveal the box and ask participants where they think the ball was dropped. So we'll do that here. And I'll drop it once more. And then I reveal the cover. And in this case, you might think now, or at least that's what our participants thought, it's very likely now that it was dropped in hole 2, because I heard the beep sound at the beginning, then it was like a boom, an impact sound, and then this sort of sand sound at the end, which makes this basically the only path that's consistent with that idea. Right, so how do we do inference now? For the visual part, we do the same thing that we've already done earlier, taking into account essentially how close the ball would end up being if it was dropped into the different holes to where it actually was. And now for the auditory part, we basically make our life fairly simple. We just think about the collision sounds, basically the vector of when the sounds happened, like in this case. So we here have a time point, a first time point where a collision happened, at time point 37. And then there was another time point where a sound happened, this last sand sound, which was at time point 77. And then we basically generate these sounds, also these vectors basically of collision sounds for all the different hypotheses. So each time we draw a sample, right, the ball basically takes a certain trajectory, ends up somewhere, but also gives us this vector of collision sounds. And that's true for all of our different hypotheses. And then we can compare what we actually heard with what we heard in the simulation. And basically, we then just assume a noisy audition model where we say like a hypothesis is good, basically if the sounds happen close to one another, but also basically then include a penalty in the likelihood that if we heard too many sounds in the simulation or heard too few sounds. So here we have for this one, we have a pretty close match. And for this one, on the right-hand side, we'd have a penalty because each time we simulate, we just hear one sound, whereas in fact, in actuality, we heard two. So if you then combine these two different sources of the likelihood, so the visual likelihood that takes into account the proximity of where the ball ended up, and the auditory likelihood that takes into account essentially how similar the auditory signal was to the one that actually happened, we find in this case that people think it was very likely that the ball was dropped in hole 2, and the model also makes this inference. So basically for the same scene here, if you just have visual evidence or you have visual and audio evidence, you make very different inferences. And this was kind of a simple example here, but in the experiment, we also had cases where multiple paths would lead to the same number of sounds, but like different delays between the sounds. And now you have to be sensitive basically to this delay information in order to make the right inference. Okay, so to recap this second part, I introduced this idea of multimodal integration, like through mental simulation. So we developed a noisy physics simulation model that accurately captures people's predictions in this task. People can use this model that they have of the situation to draw inferences about what happened by mentally simulating the different possibilities of what would have happened if the ball had been dropped into the different holes. And basically the physical representation of this world in people's mental model allows them to then bring the different sources of evidence together. In this case, the visual evidence about where the ball ended up, but also the auditory evidence about the sounds that the ball generated when it was being dropped. This project and its sort of like developments was actually funded by a seed grant from HAI. And we have taken that in a few directions now. So one way that we're doing is we're exploring the development basically of multimodal inference. So this is done in collaboration with Joseph, Sija, and Hyo. So we basically just put Elmo on top of the box and then ask children in this case to say, okay, in which hole do you think Elmo dropped the ball? Playing the same game that I essentially showed you now. And what we find that there's this very interesting developmental trend. So whereas younger children's responses are best explained by either, they're just guessing or they're just matching, basically going with the hole that was closest to where the ball ended up. Older children around 6 and 7 year olds, their answers are starting to be consistent with essentially engaging in visual simulation. And then starting around 8 years of age, children also seem to be now sensitive to the auditory signal that they hear. So integrating both vision and sound when making the inferences. And in another project led by Ari Ying Chen and in collaboration with Scott Lindemann, who's also here at Stanford, we're looking at the underlying processes now with adults and how they're making the inferences basically in the Plinko task. Again, using eye tracking here to give us a window into how people are actually carrying out these mental simulations and basically how they're kind of employing their attention to be reducing uncertainty in the visual scene. So stay tuned for that. To conclude, hopefully these two projects have sort of given you a sense of this idea that I think is very, very plausible and powerful, namely that humans build these rich mental models of the world, and that they use these mental models by running mental simulations on them, which they can then use to make predictions about the future, make inferences about the past, and also most critically for answering questions about why, evaluating counterfactuals. So together, these capabilities of having this mental model of the world and being able to run these different kinds of cognitive operations over that model is really critical, I think, for how humans at least understand why something happened. And maybe those are the kind of capabilities we also want to build into AI systems to make them more intelligent and more human-like. I had seen that one of the comments that people had posted earlier before this talk was about, to what extent this work was inspired by the philosopher Nelson Goodman. And, and in part it has. And I just wanted to put this little quote here that I really like. So in his book, Fact, Fiction, and Forecast, Goodman says that we have come to think of the actual as one among many possible worlds. We need to repaint that picture. All possible worlds lie within the actual one. So with that, I want to thank my collaborators, Josh Tannenbaum, David Lanyard, Noah Goodman, Matt Peterson, and Max Siegel, who were involved in, mainly involved in the two different projects that I talk about. And I also wanted to thank you all for your attention, and I'm looking forward to answering some of the questions that you've posted.
Awesome. Thanks for the really wonderful talk, Toby. I'll clap since everybody else is hidden from you.
Thank you.
Let's see, there's a bunch of interesting questions on Slido, and I will be your conduit for those. Let's see, let's start out with a question from Mike Liveright, who asks, are you assuming that mental simulations are quantitative, or could they be qualitative? People often appear to reason in qualitative terms.
Yeah, so that's a really good question, and a tough one too. So my sense is that so one of the things I think that humans do often extremely well is that they basically build mental models like of a particular domain that abstracts away from a lot of the dimensions basically of the real world. Right. And so sometimes we may then be able to understand these more qualitative mental simulations as essentially operating like over these more abstract representations of the world, where you might be abstracting away, for example, from notions such as time, let's say in the physical domain, or many other attributes, really, right? So I don't, even in the task that I showed, like I don't really need to pay attention to the color of the objects and so on. So one, I guess, kind of, answer to that question, although it's somewhat hand wavy, right, would be that, okay, maybe we can still understand those sort of more qualitative reasoning phenomena, also in terms of basically mental simulations, but they're just now operating over a more abstract representation over the world, where a lot of the quantitative stuff basically has been abstracted away from. That would be one idea.
Awesome. Let's see. So Johannes Eichstadt is asking about the relation between these findings and the classic moral reasoning, like the Charlie problems.
Yeah, that's a good one, Johannes. So and a little bit that I have to say like about that, and I don't know, there's a lot additionally that's going on, of course, in these trolley problems, like obviously utilitarian considerations about how many people are being saved and not, but also there's a lot of work, right, looking into basically how basically the different ways in which people are causally, the causal role that their actions play, how that affects basically whether or not we find certain things to be permissible. A lot of work, for example, about whether people harm someone as a means to bringing about the outcome, or whether the harm was just a side effect of something else that people wanted to bring about. So the notion of a side effect, of course, already then needs some sort of causal understanding, right, to realize that this was not something that played a means in bringing about the outcome. So there's a tight connection there. And there's some work basically that tried to characterize, okay, understand that notion basically of what is a side effect, and essentially linking up to this idea of intention and planning, and basically saying, well, a side effect is something that, even if it hadn't been there, that wouldn't have made any difference to your plan. So it's basically thinking about the notion of causation, but now on the level of planning, and then understanding like an intended outcome as the kind of outcome that makes a difference to your plan. So that's one connection, so that there's basically in a lot of these trolley problems that there's intricate causality going on. The other one is sort of like one of the two cases that are discussed a lot, right? It's the switch case, where somebody pulls the switch to redirect the train, and then the other one is pushing somebody off the bridge, right? And that people don't like at all, this idea. And maybe there's a little bit to be gathered there, or a little bit to be garnered, let's say, from these different aspects of causation that I've introduced, like in the counterfactual simulation model. Right, so maybe part of what makes it also bad, like pushing a person off the bridge, is that in that sense, you're also more of a how cause of the outcome, because the way that there's a sort of direct transfer basically from your action like to the outcome, and that might also make it such that we don't think that this is morally permissible. And that idea also basically that, force and contact are important is not a new idea for moral judgments. Other people have made this point, but it's sort of maybe at least as consistent with this idea that the counterfactual simulation model introduces these different aspects.
Amazing. Cool. Let's see. There's a great question from Suyog Chandramoli asking whether these models of causal attribution can also be used for causal learning, to model causal learning behavior. And Suyog raises, for instance, the paradigms by Neil Bramley and Dave Lignato, which I know you're familiar with.
Yeah, close friends and colleagues, and we've worked on a number of projects together. Also, Neil, David, and I. And so, yeah, the question of causal learning is super interesting, right? And I started saying like, oh, this is one of the things that we're also interested in the causality and cognition lab. But for both of the projects that I talked about here, I already assumed that people have like a relatively accurate model of the world. Like, but how they get there, right, is an extremely interesting question. And if the model is, you know, supposed to have basically some of the characteristics that the models have that I've been dealing with, like, for example, that it has objects and that it allows these counterfactual operations like on that objects, that also then constrains a little bit what the learning story might be, right? So there's beautiful work, for example, here at Stanford by Jiajun Wu and also by Noah, right, of thinking about learning sort of in terms of a program induction, basically. And so there, this view, of course, is sort of close to what I've been developing here, right? In the sense that people basically have a mental representation that is similar to a program in certain respects, but now we have to think about basically how it could be that people get to that representation. So that's sort of like part of and there it's just, I'm hoping that a lot of good people will continue to do that work, which will then also mean that eventually I'd be able to apply the kind of model that I've been using here in a fairly kind of restricted domain, but ideally to other kinds of more complicated or more complex settings, right? If we basically can generate causal models of those domains that have the right form, like namely objects and agents, and being allowed to then basically probe different kind of counterfactuals on those. So there's another part maybe to that question, which was asking, okay, what role does basically the process of engaging in causal attribution play like in learning, right? And that's also a very interesting question, right? So, and there's some beautiful work by Tanya Lombroso, for example, arguing that engaging basically in explanation, right, can shape the kind of learning that we do. And so, and how that would concretely kind of like play out in our account, right, is that when people make causal judgments or explain why something happened, that suggests, right, in order to do so, they don't just look at actually happened, they also have to generate these relevant counterfactual simulations. And maybe doing so, like engaging in this process, actually helps us to learn the kind of generative model of how the world works sort of more quickly. So there might be an interesting sort of like back and forth between having some alternative ways of learning the causal structure of the world, like interacting with it, or basically having explanations like generated by others, but then also engaging in this process of explaining and attribution oneself to jointly arrive at a good representation. But that still remains to be worked out.
Great. So here's a question from Imran Thobani, which I think is referring to the very beginning of the talk where you laid out this causal hierarchy. He asks, is it possible for a mental model to support counterfactual simulation without supporting causal judgments? Or is counterfactual simulation all there is to making causal judgments? Yeah, that's a great question. So I should first say that the kinds of causal judgments that I've restricted myself to, like in here, again, the causal judgments about, you know, particular events, right? As in saying like, oh, you know, what caused this ball to end up, you know, where it is here in the Plinko domain, or, you know, did this ball cause the other one to go through? So, and I think for that level, my understanding is that counterfactuals are critical, like indeed, that's the thing that we need, because we want to find out, okay, what made a difference to the outcome? And since we're just dealing with individual events, the notion of difference making, at least to my understanding, is sort of tied to this idea of counterfactuals. That doesn't mean that it's the only route, like, to getting to causation sort of in general, of course, right? So all the work, like, you know, the experimental work that we did, and the, you know, beautiful work that the recent Nobel laureate here at Stanford did, Guido Imbens, on kind of what we can learn about causality, really there just from observational studies and sort of taking into account the natural experiments that are happening in the world. So that's, of course, another route to causation, but one that applies more now sort of on what philosophers tend to call the type notion
definition of causation, right? Like smoking causes cancer, or vaccines prevent COVID. So on that level, I think you don't necessarily need counterfactuals, although ultimately you are still going to be interested in, in that level of, did it make a difference, for example, in that case, like for me? And on that level, I think you do again need counterfactuals, because it's then comparing, what did I do, and how would the world have played out if I had not done that?
Wonderful. I think we're about out of time. So Toby, thanks again. And thanks to the audience for really great questions. Let's see, I am asked to tell you about next week's seminar, which will be on the topic of Beyond Image Interpretation in Radiology, Data Efficient AI for Accelerating MRI Acquisition. And it'll be by Akshay Chowdhury, who's an assistant professor of radiology and biomedical data science at Stanford. You can register through the website. And a big thanks to everybody. Hope to see you next week. And again, thanks, Toby.
Thank you.